Hi, today we're going to talk about our paper on the quantum wreath product and Schur duality. The purpose of the paper is to study representation theory of the Hecke algebra for complex reflection group and some related algebras. In particular, what we want to deal with is the Ginsburg-Weyl-Upton-Hookear problem for this Hecke algebra. One essential step is to study a very special subalgebra of the type A Hecke algebra, what we call the Hu algebra, which first appeared in a paper by Chun-Ju, in which he states that the Hecke algebra of type D is Morita equivalent to some type A parabolic plus this Hu algebra. And our slogan is this Hu algebra should be considered as the Hecke algebra for the wreath product. Sn wreath S2. In general, there are not even Coxa groups. To do so, we need to establish a new notion which we call the quantum wreath product. And hence, we'll have a uniform treatment to variants of the Hecke algebra given in the list. Let's come back to the GGOR problem. The goal is to construct nice highest weight covers for these Hecke algebras. It is proved by GGOR that such a highest weight cover can be constructed by considering the KZ functor from the category O of a rational Schur algebra. In the same paper, they conjecture for type A under certain conditions, this highest weight cover can also be obtained by considering the Schur functor of the module category over the Q Schur algebra defined by James. In other words, this diagram commutes, and this very complicated KZ functor can be realized by something that's explicit as patterned by an idempotent. We can then phrase the GGR problem beyond type A. That is, we want to construct finite dimensional algebras SW such that this diagram commutes. In particular, we can realize this KZ functors using some variants of the Schur functor. Such a problem in type B has been done by combining a result by Hookear and our previous work. The key step is to construct this Schur functor inspired by the following Morita equivalence between the type B Hecke algebra and some products of type A parabolic subalgebras. Therefore, one can hope that this approach can work for the complex reflection group of type GPPD, because there is already a Morita equivalence available due to Chun-Ju and Hu massas. In particular, for type D, there is such a Morita equivalence. And then the question is, we want to understand the representation theory of this very special Hu algebra. We first recall that as a group, the wreath product of Sn by S2 can be generated by simple transpositions S1 to Sn minus 1, altogether with an extra generator small case t, which permutes the first m integers with the latter m integers. Then the Hu algebra is defined to be the subalgebra of H of S2m generated by this maximal parabolic subalgebra together with an extra generator small case Hm. So that the dimension of this subalgebra equals to the order of the wreath product. This property does not come for free if you choose, say, the standard basis element corresponding to small case t. The subalgebra generated by such an element will have, in general, a larger dimension than the order of the group. While Chun-Ju proved that there is an element satisfying the dimension property, he did not have an explicit formula for this extra generator Hm. This is then our first technical result. We obtain an explicit formula for this extra generator, and then the central element, which equals to the square of this Hm. For the simplest case where n equals to 1, the extra generator is the sum of the standard basis element together with its inverse. And the central element is equals to quantum 2 squared. For m equals to 2, this is already complicated enough. Hm is the sum of 4 terms. Each term corresponds to a possible configuration of a thickness 2 strand. By that, I mean each crossing can go over or under all the other m crossings. And then if you look at this formula, you wouldn't believe it, but if you square H2, you actually get an element in the center, which is only spanned by T1, T3. While we don't have a simple formula for this central element Zn, we know that it acts on Schur modules by this product of quantum 2 squared with a different subscript. With this explicit formula, we are able to describe a presentation of the Weyl algebra, which is generated by a tensor product of an algebra, a generator H1. The relations are given by a quadratic relation, H1 squared equals to Zm, as well as a wreath relation, basically saying H1 is an intertwiner for element in the maximal parabolic. It is very important that the coefficient in the quadratic relation here is not only in the ground field. We need a quadratic relation in which the coefficients are elements in B tensor B. So we look back to the well-known notion of the wreath product. You take a base group, take its direct product. You produce a group generated by the direct product altogether with the simple transpositions, subject to the Bray relations, quadratic relations, and the wreath relation. Then, by a quantum wreath product, we mean an algebra denoted by B wreath Hm. You want to take a base algebra B. This can be non-commutative. For example, the Hecke algebra or the ring of Laurent polynomials. Then you take the tensor product of B. You generated this algebra using the tensor product as well as Hecke-like generators HIs. The relations here are the same Braid relations in type A, but the quadratic relations are deformed this way so that the coefficients lie in the tensor product of the base algebra. In order to accommodate more examples, we also deform the wreath relation so that it also accommodates error terms rho. Here, sigma and rho are some endomorphisms of B tensor B. And voila, we have now a definition of an algebra we call the quantum wreath product. Let us go over some important examples. For some quantization of finite groups, we have the Weyl algebra, which can be considered as the Hecke algebra of the wreath product Sm wreath S2. For the other wreath product, the cyclic group wreath the symmetric group. This is also the Yukonuma Hecke algebra that can be considered as a quantum wreath product. By the way, the Ariki-Koike algebra can also be considered as a quantum wreath product. More importantly, we don't have to restrict to finite dimensional algebras. Think of the extended affine Weyl group of type A as the wreath product of the group of integers wreath Sn. And hence, the affine Hecke algebra of type A is now a quantum wreath product of the ring of Laurent polynomials wreath Hm. And then the wreath relation is precisely a paraphrase of the well-known Bernstein-Lustig relation. You can go further from the affine Hecke algebra. For example, Wittgenstein's rho-p Hecke algebra over this p-adic group is also a quantum wreath product. Also, it doesn't have to start from a group algebra. For example, Kleshek-Moof's affine zigzag algebra is a quantum wreath product. The list doesn't stop here. Our quantum wreath product happens to include the following important algebra in these papers. In our paper, the first main theorem is about the structure theory of the quantum wreath product. We obtain the necessary and sufficient conditions such that the quantum wreath product have a PBW basis, which means for future algebras, which are quantum wreath product, you don't have to reprove the basis theorem from scratch. You can just check that the coefficients in the relations satisfy the conditions given in our first theorem. Our second result regards the representation theory of quantum wreath product. Suppose that B is a symmetric Frobenius algebra and some technical condition holds. We show that one can obtain a Schur-Weyl duality for the quantum wreath product by lifting the Schur-Weyl duality of the base algebra. As a corollary, we obtain the Schur-Weyl duality for the whole algebra or group algebra of the symmetric group Sn wreath S2 for the first time. Our theorem also recovers quite a few Schur-Weyl duality in the literature. Let me summarize with some slogans. The first one is the Heck algebra now makes sense beyond complex reflection groups. Secondly, we believe this foundational paper will lead to many consequences. We believe that one should consider questions regarding quantum wreath product in a uniform approach. One should ask, what's the conditions for the parameters such that the property for the base algebra can be lifted to properties regarding the quantum wreath product. We have done this for the existence of PBW basis, the symmetric algebra structure, and the Schur-Weyl duality. There are more properties for a quantum wreath product that we are to explore. You will see some of them in the sequel of this paper. I'll stop here. Thank you for your time.